All right, so today's lesson, we're going to be adding vectors, and we're going to learn how to do that. So let's say we have two vectors, A and B. Right, in this case, A is just AC. I'm just labeling it as a vector A, and B is AB. Now you can have them anywhere, just like down here. But how we're going to add them is if we connect them tail to tail, just like this. And then we use an equal vector to B up here and an equal vector to A over here, and we're sort of completing the parallelogram. And the diagonal that goes from where they connected tail to tail over to where these two vectors connected tip to tip is going to be what A plus B is. So you can imagine that if you're just walking, let's say you're here at A, and you decide to go to school, which is over here at D. But you want to go to the convenience store first, and the convenience store is over here. So what you do is you walk to the convenience store, and then you walk over to school. But essentially, the displacement that you've covered from one point to the next was from here to here, from home to school. Okay, and you can add any type of vectors. You can add like displacement vectors or velocity vectors or force vectors or any sort of vector you want. As long as you're not adding, say, a force vector to a velocity vector. That doesn't make sense. Okay, but we'll get into applications later. And you can see, if we just look at part of the parallelogram, right? If we just look at this portion here, we have a triangle. That was a terrible line. That was even worse. But I have it drawn down here, right? Where if this is theta, some angle in between, well, that's not theta. The whole thing will be theta if we have B here. That's theta. This angle here, since it's a parallelogram, is 180 minus theta. So you can see if this is just a triangle and we know what this length is and we know what this length is, and if we knew what the angle between them was, we can calculate this angle, and therefore this is a cosine law problem. We can figure out the magnitude of that vector using cosine law. All right, well, what about subtracting vectors? Let's say here you have A and here you have B, and you wanted to subtract them. Well, the easiest thing to do is just to take B and figure out what negative B is by flipping the direction, and then simply doing A plus negative B. Okay? And you can create a triangle, right? So you can create your triangle, right? Adding tip to tail. There's A. Here's negative B. Again, I messed up with my straight line, but you can see it. Right? And then your starting point is here. Your ending point is here. Now you can see this in a different way if you like. If you connect them tail to tail like this, which is what I was trying to draw earlier, right, where this is A and this is B, then what you can do if you rearrange this problem, right, if you go B plus A minus B, that'll give you A. So what you're doing is you're trying to figure out, okay, what combination or what vector here do I need to add to B right here in order to get back A? Like this. Right, so there would be A, B, and there's the subtraction of both. All right, so if everyone's good, we're going to try figure out what this is. So here we have three vectors, A, B, and C. And we're going to try figure out what A minus B plus C is. So let's just work with A minus B first. So negative B would be just B, but I'll draw it in the opposite direction. There's negative B. And then I can take A. I'll just try and redraw it down here. So there's A. And then I'll add B to it, going from the tip of A to the tail of negative B, like this. All right. And that here would be A minus B. Next, if I want to take A minus B and add C, I'll just do that over here. Here's A minus B. And if we're going to add C to it, you add C here. And this is what we end up with. A minus B plus C. Where this was our A minus B, and this is our C. Now we could have done this all at once if you wanted to. It makes it a little bit more challenging because if I did A here, like this, and then we add negative B here, like this, then what I could have done is I could have then added C here, like this, and we would get this vector here, where that vector there is the same as this one here. The only difference is it's a lot easier to solve this triangle and to use this information to solve that triangle as opposed to trying to solve whatever shape that is right there. Right? So if we're trying to solve for the magnitude of that length, this shape makes it quite difficult. So I'll do a little recap and I'll explain. So some good questions. This is the way we're doing it in this class. So again, I'll just recap. If you have any vector like A and B over here, you can move B here and create your parallelogram to find the sum by connecting tail to tail. Or you can connect the tip of one vector to the tail of the next and create a triangle. Either way you do it, you're going to use sine and cosine law to solve it. Now the other way to do it, which is technically more done in physics, is to create components of each vector. And I'm going to introduce you to that style of doing it in lesson 4 of this chapter. And it is a lot easier to use components when you have a problem like this one here, right? Where you would have to create 2 triangles otherwise to solve using sine or cosine law. Components can make things like this easier where you're adding more than 2 vectors together. However, in this class, most of the time we don't deal with this. We deal with adding 2 vectors together and we form a triangle and we do cosine law. Can you use components to solve it? As a physics teacher, I love components and I make my physics class do components. Would I want all my physics students to continue doing components in calculus? No. And the reason why is because if components is the only method you practice and it's the only method you get good at, then when faced with a new problem that you haven't seen before, you only really have one tool to attack it with. And I do know of some problems that if you really want to, I can give you, where you simply add 2 vectors and suddenly using components, you need to be a master at trig identities to solve it. And it's really tricky. But sine and cosine law, you can do it like that. And I can find other problems that are the reverse, where components would be easier and sine and cosine law would be difficult, right? Just like this problem here that I'm mentioning. So if you've learned components and you're comfortable with components, that's great. All the more reason why you should not use components in calculus, though, if that makes any sense. All right, so we're going to try do some practice problems then. See if we can understand this better with some examples. So here we have 2 vectors. Let's call this B and A. Again, different from the previous question. Now A has a magnitude of 3 and B has a magnitude of 2. And we want to find out what it would be, what the magnitude would be for A plus B. So what we can do is sort of complete the parallelogram. So we'll use an equal vector to A. I'm doing my best here. Oh, not bad. Okay, and an equal vector to B. Right, notice that we connected tail to tail. Or you can think of it as your triangle connecting the tip of A to the tail of B right here. And if we complete the diagonal in our parallelogram, right, we know that this angle here is just 180 minus 60, which gives us 120 degrees. Now this is our A plus B. So we can solve for the magnitude of A plus B using the cosine law. So the magnitude of A plus B squared equals the magnitude of A squared plus the magnitude of B squared. And I'm running out of room, so I'll just write it here. Minus 2 times the magnitude of A times the magnitude of B times the cos of 120. Okay, and make sure that is degrees, so you don't use radians on your calculator. So the magnitude of A squared, that's just 3 squared, plus the magnitude of B squared, so that's 2 squared, minus 2 times 3 times 2 times the cos of 120. And if you reduce all of that, you should get 19. Okay, but remember, that's the squared of the magnitude. So square both sides, and we'll get the magnitude of A plus B as the square root of 19, which is approximately equal to 4.36. So there's the magnitude of the sum of A plus B. All right, so I had a good question. Why don't I connect the diagonal this way? So let me go back and explain. In our first example, zoom in so we can see. All right, so we take any vector, right? In this case, we have B here. Now this part is called the tail, and this part is called the tip. And what we're going to do, two ways to do this. One, connect the tail of B to the tail of A, just like I have here. Right, so I have this shape. Then you complete the parallelogram by putting equal vectors of A here and equal vectors of B here. Then you're always going to start where the two tails meet, here. And then to where the two tips meet. So from the tails to the tips. Right? However, another way to do it is to write A here and then translate the tail of B to the tip of A, which is essentially what we have here in our parallelogram, right? So here's the tip of A, and here is the tail of B. Right? So we just connected tip to tail, and then we connect from where we started off at A to where we finished at B. You get the same result, right? So we're doing the same thing here. Let me zoom in again. So we created our parallelogram by connecting the two tails of A and B, and then drawing equal vectors, and then connecting both tails to both tips. Now you can look at this the other way as well if you're just looking at this one triangle here, where you have vector A, and then connecting the tip of vector A to the tail of vector B here, and then going from where we started at the tail of A to where we finish at the tip of B, right? Either way works, but drawing a vector this way that doesn't quite work. I'm not quite sure what you'd be solving for there. Well, if you had negative A in the opposite direction and then B here, right, then you would get that other diagonal. And so what you're really solving for, if you take this other diagonal, which would be going from, I'm using so many different colors here, going from here to here, you would be solving for b minus a. Okay, so be careful not to take the other diagonal, because then it's going to be like what we have up here. All right, next good question. Where does the 120 degrees come from? I'm going to use a different color if I have one. Okay, if you're using a triangle, remember this is not 60 degrees. The entire thing here is 60 degrees. So you have to think of this as your parallelogram. Now in a parallelogram, all angles are going to add to 360. And in fact, this will also be 60. And this angle here, let's call this one theta, and this one theta. So really you have 60 plus 60, which is 120, plus 2 theta must be 360. An easier way to do it is just to realize that this angle and this angle would add to 180. So if this is 60, then we figure out what theta is by doing 180 minus 60. All right, so let's move on to question 3 then. So in this question it says, here we have this wonderful rectangular box, and we're going to express each of these vectors in terms of A, B, and C here. So B and C, or BC. So where's BC? BC is here. There's BC. So in this case, right, we can express it as here's A. Technically AB over here is the same as B. Okay. So that'll help us later. But BC is the same as A except in the other direction. So that's just negative A. So for part A, we can express that as just negative A. GF, where's GF? GF is all the way up here. GF is identical to A. It's just translated to a different position, but same length, same direction. That one's just A. Okay, OB, where's OB? OB is right here. Notice we have our parallelogram here, right, where we have A plus B. So that's just going to be A plus B. Next we have AC. I'm going to start using a different one. I'll use red. AC is this one here. So this is like the question we had before about taking the other diagonal. When you take the other diagonal, what we're doing is B minus A. Right here, B minus A. Notice the direction that all the vectors are pointing for B and minus A. Right, connecting tip to tail, right, and starting at the tail of B, ending at the tip of minus A. So B minus A. Next, BG. Where's BG? Right here. So here's B, and G is up here. So in this case, we have C. So we can imagine C being right here. And you can think of this in terms of, again, this is A, but if we took negative A and went from here to here and added tip to tail here, then we would get BG. So that would be negative A. So BG would be C plus negative A, or C minus A. And last, OF. Here's a fun one. Going from here all the way across. So what are we doing here? In this case, first let's look at it as OB. OB is A plus B. We already have that. OB is A plus B. And if we take OB and add BF, which is C, then we end up with OF. So we just need to add C there. Okay, any questions? Okay, so I'm just going to go over the last question. We are going to go over this in class tomorrow, but I just wanted to get it on the video for this lesson. So here we have an airplane, heads due south at a speed of 300 kilometers per hour and meets a wind from the west at 100 kilometers per hour. What is the resultant velocity of the airplane relative to the ground? So to figure out the resultant velocity, let's look at what these are. I'm just going to draw them. Here we would have going south at 300 kilometers per hour. I'm just going to label that V. Let's call that the velocity of the airplane. And then the wind, we have something that says from the west. So be careful. If it's coming from the west, it's going to the east. So I'll make that length smaller. I don't have to draw a to-scale diagram like we did in the previous lesson, but do make sure that if one has a smaller magnitude, that the vector is somewhat smaller. And I'm just going to label that W for the wind velocity. Now to figure out what the ground velocity is, we just need to add these two vectors. So what I can do is, again, two ways. I can connect their tails together like this. Oh, that was terrible. It's not easy drawing on this. Okay? And then you can just complete the parallelogram, which in this case is a nice rectangle. And there you go. So if we just look at this part right here, we see a triangle. So let me just redraw it because it'll be easier to analyze a triangle. So here's our triangle portion, where here we have V, here we have W, and here we have the ground velocity. Let me just label it G. Okay, and this is a nice problem because it's nice a right angle triangle. So we don't have to do sine and cosine law. We can do Pythagorean theorem to figure out the magnitude. So let's start with that. So the magnitude of G squared will equal the magnitude of V squared plus the magnitude of W squared. Okay, which is 300 squared plus 100 squared. This would be 90,000 and 10,000, so 100,000. Okay, remember, that's not your final answer because that's the magnitude squared. So let's take the square root of both sides. And we get the magnitude of our ground velocity to be about 316.23, but let me just round off there, kilometers per hour. Now, it's not just enough to know how fast a plane's going. We need to know where it's going. So what we actually need to do is figure out what that angle is right there. Because it's heading some southeasterly direction, but where exactly, how many degrees east of south is it actually heading in? So to figure that out, which is this angle here, I'm just going to use our tan ratio because it is a right angle triangle. So tan of theta equals opposite over adjacent. So we have the magnitude of W over the magnitude of V, which is 100 over 300, which is just 1/3. And so you can calculate theta if you take the inverse tan to be 18.4 degrees. I'll just leave it as 18. So then we can say that our vector G is 316 kilometers per hour. And then usually we write direction inside of square brackets to indicate the direction of that vector. And in this case, it's heading south 18 degrees to the east. That's one way of writing it. We could also write east 18 degrees of south, or we can write the bearing, and the bearing is, if I go back up here, the bearing, if we have our compass coordinate system, where this is north, the bearing would be the angle taken from north going clockwise all the way over to our vector here. So if this is 18 degrees here, and we can figure out that this would be 162 degrees. So our bearing would just be 162 degrees.